There's two other special quadrilaterals that we need to talk about, and those would be the kites and the trapezoids. These are not parallelograms, so they don't fall under the parallelogram umbrella. Let's start with a kite. A kite is a quadrilateral with exactly two pairs of congruent consecutive sides. Consecutive sides, so those are sides that are next to each other. Let's look at a picture. So here's a picture of a kite, and we have the consecutive, let's draw an arrow. So we've got these two consecutive sides are congruent, and then separately these two consecutive sides are congruent, but those are not congruent to each other. Now we have non-vertex angles. Those are these two angles here between the two sides that are not equal, the two sides that are not equal. And then we also have the other angles are called vertex angles, and those are the angles that are between the congruent sides. So those two sides and these two sides in between there. Let's look at some properties for a kite. First thing is the diagonals are perpendicular all the time. So if you drew the diagonals, I think it would be pretty clear you could see that they form 90-degree angles. What else do we have? Exactly one pair of opposite angles are congruent, and those would be the non-vertex angles. So let me move this out of the way for a minute, and this. So when you have a kite, those two angles are always going to be congruent. And I think if you draw it so these two sides are a lot longer than these two sides, I think it'll be clear that this angle up here is not going to be congruent to this angle down here. This one's narrower because these sides are longer. This angle here is bigger because these two sides are shorter. But these non-vertex angles are always going to be congruent. So we've got diagonals are going to be perpendicular. The non-vertex angles are congruent. One of the diagonals bisects the opposite angles. Let's take a look at that. Move those out. So one of these diagonals bisects angles. I'll move this right there. All right, and I think if you look at it, this angle here is going to be smaller than this angle. So this diagonal is not bisecting this angle. But these two angles are congruent. And these two angles are congruent. And that's pretty easy to prove. So here's one thing you can do, is you can draw in one of the diagonals that goes through the vertex angles. And that side is congruent to itself. So we actually have two congruent triangles by side, side, side. And therefore, that means that all the corresponding parts are congruent, which would make this angle here congruent to this one here. My diagonal's a little crooked. This angle here is going to be congruent to this angle here. So this diagonal is bisecting these two angles. The other diagonal does not. And we also have that these two angles, these non-vertex angles, are congruent as well, because these two triangles are congruent. So if you get stuck on the properties, sometimes it helps. Draw in this one diagonal here, and then you should be able to see all these other properties. And we have another one. One diagonal is the perpendicular bisector of the other diagonal. So let's go back to here. And if I draw my other diagonal in here, we know already that they're perpendicular. But does it look like this shorter diagonal is cutting this longer one in half? No, it doesn't. But the longer one is cutting the shorter one in half. These two pieces here are going to be equal to each other. So that's another thing that's true. This one here is equal to that. So one of the diagonals bisects the angles. It also bisects the other diagonal. They're perpendicular to each other, and the non-vertex angles are congruent. So you have to go through a few times, and the more problems you practice with, the easier it gets to remember these properties. So let's look at an example. KITE is a kite, so that's given to us. And they're telling us some of the angles. So they tell us that the measure of angle EKT is 27 degrees. E to K to T, that's right up here. This one is 27 degrees. Well, immediately we know this one here is 27 degrees. All right, what else do they tell us? The measure of angle KET is 104. K to E to T, that's this entire angle here, is 104. I need to move the 104 so it's easier to read. So KET, this whole thing here, 104. And we know that angle is not bisected, so we can't just cut that in half for the two angles. We also know, therefore, this one across here is 104. All right, they tell us K to I is 8. So this segment is 8. And therefore, we know this one is 8 because these are equal to each other. And these will be equal to each other. And I to T is 12. So therefore, we know E to T is 12. What else do we know? We know the diagonals are perpendicular, so these are all right angles. And if we look at any one of these triangles, let's look at this one for example, K to N to I. We have one angle is 27 degrees, and this one's 90, so we can find this one. We know this whole thing is 104, but I can find just this angle in here, the smaller one. So that angle right here, if I subtract 27 and 90 from 180, what am I going to get? 63 degrees? And so if I know this angle is 63, so is this one over here. And if the whole thing is 104, then I can figure out this other part of the 104 angle by subtracting 63 from that, and that'll give me the other part. So let me do that. So 63 from 104 gives me 41. And so likewise, it's the same over here. This one's 41, and this one's 63. And I can keep working my way around with the triangles now. If this is 41 and this is 90, I can get this one. So subtract 90 and 41 from 180, and that'll leave me with this angle. Notice I'm not even looking at what the questions are asking. I'm just filling in as much as I can. So this will be 49 degrees, and therefore so will this one over here. So basically this kite, if you fold the left half onto the right half, they will match. So if you remember that symmetry, it's easy to get all these things. Okay, so now we can go ahead and answer these questions. Find the length of E to T. We figured that out. That's 12. Find K to E. That's 8. Find the measure of K to N to E. K to N to E. That's our 90 degree angle. The measure of angle NET. NET was 41. ETI, E to T to I, that would be 49 plus 49 at the bottom here. E to T to I, it's both of these together, so that's 80, 98. And E to K to I, that would be this vertex angle up here at the top, both of these combined, E to K to I, and that's going to be 27 plus 27, which is 54. And one last one, the measure of angle KEN. K to E to N, we figured out was 63 degrees. So with these types of problems, I like to just go ahead and fill in the picture with everything I can figure out, and then worry about the specific angles that they're asking about. All right, let's look at trapezoids. A trapezoid is a quadrilateral with exactly one pair of parallel sides. Exactly one pair. If it has two pairs of parallel sides, it's a parallelogram. But if only one of the pairs is parallel and the other is not, then we have a trapezoid. So we have some terminology here. Usually we draw the trapezoid where the two parallel sides are top and bottom. But we could rotate this 90 degrees, and then the parallel sides would be on the left and the right. So don't always think that top and bottom have to be the parallel sides. Depends on how it's set up. Okay, so we've got the bases are the two parallel sides, so we call those the bases. The other sides are called the legs. And then for each of the bases, for this base we have these two angles associated with it, the two angles that it touches, and that's one pair of base angles. And at the top we have a second pair of base angles. Now there's not a lot that's true about a trapezoid like we've had with all our other special quadrilaterals. So all we know is that the two bases are parallel, and from what we learned with parallel lines, we know same side interior are supplementary. So these two angles will be supplementary, and these two angles will be supplementary. But these two angles don't have to be equal, nor do these two. So the only thing we have is same side interior angles are supplementary. So for example, if I knew this angle was 110, I could figure out this is 70. But I know nothing about the other two. So not nearly as much as we could figure out with a parallelogram. On the other hand, if the legs wind up being equal, then we have what's called an isosceles trapezoid. And then we have some more properties that are true. So most of the problems you'll see about trapezoids, it'll be with isosceles trapezoids. And that's where these two legs are congruent. Now when that happens, what are the properties? Well, if you just look at it, for example, now we already know these two angles add up to 180. But it turns out this pair of base angles will be equal, and this pair of base angles will be equal. So if this is 100 degrees, so will that be. And if that's 100, this one would have to be 80. So they add up to 180. And if that's 80, then so would this one. So now if I just tell you one of these four, if it's an isosceles trapezoid, you can get the other three angles. What else is true? Well, we've done a lot with diagonals. If we draw in the diagonals, what's going to be true about that? Well, let's take a look and see what they would look like. Now those diagonals obviously do not bisect each other. This is going to be a lot shorter than this one. They don't look like they're perpendicular to each other either, so that's not true. But what is true is the lengths of the diagonals wind up being exactly the same. So this one is equal to this one. So we have that. All right, so the diagonals are congruent, and each pair of base angles are congruent. Let's look at an example. TRAP is an isosceles trapezoid. Find some stuff. Well, let's just find everything we can figure out right off the bat. Because it's an isosceles trapezoid, and these are my parallel sides, these are my legs, and I know because it's isosceles, the legs are equal. So if that's 16, so is this one. I also know the base angles are congruent, so 64, this would be 64. And I know between the parallel lines, these are supplementary, so these add up to 180. So 180 minus 64 is 116 degrees, and so is this one, 116 degrees. Now I can answer the questions. What's the measure of angle P? 64 degrees. What's the measure of angle A? 116 degrees. Measure of R? Also 116. And what's the length of PA? 16 units. And that's it. Pretty straightforward. All right, sticking with trapezoids, we have a special segment called the mid segment. And because it uses the word mid, you can think midpoints, and that's exactly what's going on. If we connect the midpoints of the legs in a trapezoid, it doesn't have to be isosceles trapezoid. So this is the midpoint of this leg, and this is the midpoint of that leg. And notice I have different markings. I don't know that if this is isosceles, so I know these two segments are congruent, these two segments are congruent, but unless it's isosceles, these are not going to be congruent. so that doesn't matter. But I want to focus on the length of this mid-segment. First of all, it's going to be parallel to the bases. So I have my bases are parallel. If I connect the midpoints of the legs, that's also going to be parallel. So everything we know about angles and parallel lines applies here. It also turns out that the length of that mid-segment is going to be the average of the lengths of the two bases. Oops. So if I take the length of this base and the length of this base, add them up and divide by 2, that'll be the length of the mid-segment. It's the average of these two bases, the lengths of those bases. So let's look at an example for that. Fine, now notice I drew this one sideways just so you're not always in the habit of the parallel sides being top and bottom. Find the length of EF. So I notice from the information that they give me that E is a midpoint of AB because these two segments are congruent, and F is a midpoint of DC, these two segments are congruent. So EF is a mid-segment. Therefore, I know it's the average of the lengths of these two bases. So all I have to do to get the length of EF is add my two bases and divide by 2. So EF is going to be 19 divided by 2. And what's 19 divided by 2? You can leave it as 19 over 2, or you can write it as a decimal. Either one's fine. Most people would probably write the decimal. All right, let's look at another example. Given trapezoid ABCD with bases A, B, C, and D. So let's draw that. So we have AB and CD. Not the best drawing in the world. All right, so these are the bases, so those are parallel. If AB is 13 centimeters, this one has units on it, and DC is 35 centimeters, find the length of midsegment XY. Well, if it's a midsegment, we know it joins the midpoints. We don't know. X could be on either. X and Y we can switch. The order doesn't matter. So find the length of XY. Well, since it's a midsegment, it's the average, so all we do is add 13 plus 35 and divide by 2. And we get 48 divided by 2 is 24. This one had units, don't forget that. And there's your answer. So the only difficult thing was making sure you drew a decent picture for that. All right, last example. We have a trapezoid TRAP. The bases are TR and PA. So we know that these are the parallel sides. And midsegment EZ, find PA. Notice on this one, they didn't give us the other base. I'll just call that X. But it's still the same idea for the calculation. I know that the midsegment, 27, is equal to the average of the bases, so 21 plus X divided by 2. So a little more work, but I just need to solve this equation. So I'm going to multiply both sides by 2 to cancel those. So I'm going to get 54 equals 21 plus X, and then subtract 21 from both sides. And that's going to give me X is equal to 33. There's no, or there are, so 33 millimeters is the length of PA. And that's all there is to it. Now, there is another way to work this out, and I think it's a little easier. Since we know the midsegment is half the distance to from top to bottom, how far is it from 21 to 27? Well, we'd have to add 6. So to get to the bottom, it's the same. We would have to add 6. 27 plus 6 is 33. Well, that seemed like it was a lot easier, and it was. So there's kites and trapezoids.